Welcome to episode number 10 of my exercise series Introduction to Physics. Today we are going to focus on exercise number 2 with respect to the mechanics of fluids. But compared to last time, this time we are going to focus on flowing fluids. So we are going to talk about Bernoulli's principle. So let's have a look. A water pipeline in a house consists of two connected sections that have different cross-sections. The section in the basement has a diameter of 20 centimeters and on the first floor of 1 centimeter. The height difference is 8 meters. What is the static pressure in the pipe in the basement when the corresponding pressure in the pipe on the upper floor is 100 kilopascal and the associated flow speed is 6.5 meters per second? Out of the text, we know that we have these two different cross-sectional sizes. D1 equals 20 centimeters in the lower part in the basement and D2 equals 1 centimeter in the first floor. Then we know we have a height difference of 8 meters and we do have another given variable, which is the static pressure P2 of 100 kilopascal, and in addition the associated velocity of the water V2 equals 6.5 meters per second. Now, of course, these values are not all given in their basic units. So let's convert them. D1, 20 centimeters equals 0.2 meters and D2, which is 1 centimeter, equals to 0.01 meter. In addition, we have to recalculate the static pressure P2, and since it's given in kilopascal, we have to multiply it with 1000, making it 100,000 Pascal. And we are searching for the static pressure P1. So in order to make it a bit clearer, let's make a little sketch. You can see here that we have these two differently sized pipes. One is at the lower left-hand side and the other one on the upper right-hand side. They are characterized by a different diameter and we have associated different velocities, different flow velocities V1 and V2. In addition, we also know that between the different pipes there is a certain height difference. So basically they are on different height levels. Is this enough knowledge to solve the problem? Well, let's make it simple. For fluid dynamics, we know that Bernoulli's principle holds. It basically says that an increase in speed of a fluid corresponds to a decrease in static pressure or a decrease in the fluid's potential energy. What does it mean? Well, basically the sum of all pressures is always constant. So we have the static pressure P, we have the also kind of static pressure, which is due to the fluid's potential energy, which is the product of density of the fluid ρ, gravitational constant G, which equals to 9.81 meters per second squared, and we do have the height of the fluid column. In addition, we have another term which comes from the density ρ, and it takes the flow velocity v into account, and it's precisely ρ divided by 2 multiplied with v squared. And the sum of all three terms is constant. So we do have two static pressures and the dynamic pressure due to the flow speed. What does it mean for our present case? It means that when we compare the sum of all pressures in the basement with the sum of all pressures in the first floor, the total sum is constant, meaning P1 plus rho times G times H1 plus rho divided by 2 multiplied with V1 squared equals to P2 plus rho G H2 plus rho again divided by 2 multiplied with the corresponding velocity V2 squared. Now, this looks like we are going to need lots of parameters. So let's make it step by step. First of all, let's put all in blue the given variables and values. What is given? We know that the density rho of water is a constant. Usually for normal water without any additives, the density is 1 gram per centimeters cubed or 1000 kilograms per meters cubed. What else is given? Well, we know that G is the gravitational constant, and as mentioned before, it's 9.81 meters per second. Then we've given the height difference. So strictly speaking, we haven't been given H1 and H2. But you can see here already that if we take the second term on the left-hand side and we put it on the right-hand side, then we can calculate H2 minus H1, and this is the height difference. So technically speaking, we can take those two terms together and we've got the height difference. So it's also given. What about the remaining 4 parameters? Well, P2 was given, as was the velocity V2. So all in all, we have 2 unknown variables. The pressure P1 that we actually want to calculate, and in addition the velocity V1. Well, then we need some additional knowledge apparently. There is another thing that's constant, which is the volume flow rate. And the volume flow rate is usually written as Q, and Q being constant is the product of flow velocity V and the cross-sectional area A. Which means that if you have a tube that's changing diameter, changing size, the smaller the cross-sectional area, the larger the flow velocity. For the present case, it means that V1 multiplied with A1 equals V2 multiplied with A2. Now, we didn't have the cross-sectional areas given. We had the diameters. So assuming it's a normal pipe, usually a pipe has a circular shape, which means that we can substitute area by pi divided by 4 multiplied with the respective diameter squared, which is done here. Now we see that both on the left and right hand side we have this pi over 4, so it cancels out. And what we have is V1 d1 squared equals V2 d2 squared. And if we do the same as in the first equation on this slide and we color all our given variables, then we see that the diameters are both given and we know the velocity V2, so we can, strictly speaking, directly calculate the velocity V1 of the fluid in the basement. In addition, we can take this equation now and put it into the top line. And what we get if we put all the given variables on the right-hand side of the equation and our only unknown variable P1 on the left-hand side is shown here. We have P1 equals P2 plus rho G introducing delta H plus rho over 2 multiplied with velocity V2 squared minus rho over 2 multiplied with the velocity V1 squared, and we've substituted V1 by d2 squared divided by d1 squared multiplied with v2. Of course, we can rewrite the third and fourth term on the right-hand side and put them together. Then we have basically three terms on the right-hand side. The static pressure due to the height level, and the dynamic pressure due to the differences, basically. It's not the absolute pressure, since we're talking about already the differences between the different sections. And if we calculate all three terms, we can do it quite easily, because initially we wanted to calculate all our given variables and values in their basic units. So we can put them all in the calculator right here. And what we get is that P1 equals 100,000 Pascal as given, plus 78,480 Pascal, plus 21,125 Pascal. All in all, this makes 199,605 Pascal. Of course, we could leave it at this, but looking back at the initially given variables and values, we realized that, for example, the static pressure P2 was given as 100 kilopascal or 100,000 Pascal. So maybe it's a good idea to rewrite or round this value, this 199,605 Pascal, and say that P1 equals 200,000 Pascal. So what do we learn out of this? Well, firstly, if you do have a constant volume flow, then it's really easy. The larger the cross-section of a pipe, the slower the flow. On the other hand, if we are considering pressures, then it's more complicated, because we do have static pressure and we do have dynamic pressure. And of course, as part of static pressure, we do have the pressure of the liquid column itself. So it's a bit more complicated when we're thinking about complex problems. But all in all, Bernoulli's principle really helps us to actually calculate flow velocities as well as pressures in pipe systems. And with this, I would like to thank you for your kind attention. I hope it helped you, and if it did, I would be most happy if you subscribe and give a thumbs up. And if you still have some question, let me know in the comments below. And I hope to see you soon for the next video. Bye!